Okay, the second part of the video now, we're starting with continuity, which is where a function is continuous if you can draw it without picking up your pencil. And it's discontinuous if there's a place where you'd have to pick up your pencil to continue drawing that graph. So there's two types of ways that something can be discontinuous. It can have a hole, or it can have a jump, or it could have more than one of either of those. If it has a hole, that's a removable discontinuity because it's only at that one spot that the graph does something weird and has just a hole there. Otherwise, if we took that out, if we removed that discontinuity, then it would actually end up being continuous. What happens on an equation that would cause that is if you have something that you can factor on the top and the bottom where something would cancel out. So like if I have this equation, which I've already factored on the bottom, I could cancel out these x's. So I could cancel out these x's right here. And because I can cancel those out, that means that there is a hole where on the bottom we have x equals 0. Or on the top, either one. At that spot, there's a hole that the graph just doesn't have a value there. A jump is considered a non-removable discontinuity because it's not something we can just take out and it would be continuous. And on an equation, that's the part that's left over here, is a jump that I could say x minus 3 equals 0 and find out where that jump is, because those are vertical asymptotes, which we'll talk about later a little bit more. Okay, so that's the difference as far as what the equation looks like. Let's look at an example with a graph. This graph up here on the right, we want to know, is it continuous or discontinuous? And so if I look at it, I can draw right here, but then to keep going, I would have to pick up my pencil and move it up here to keep drawing. So that means that this is discontinuous, and we want to know where it's discontinuous at. Well, if I look at my graph, it's discontinuous right here. Looks like a vertical asymptote right there at x equals 1. Okay, and then this would be considered a jump because we're going down, 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 and then we jump way up here, and then we keep going down. So for my answer on this, I would say that we have a non-removable discontinuity at x equals 1. That would be my answer there. That tells them all the information that they really wanted to know. Next, we want to talk about max, min, increasing, and decreasing. So on this graph, we have some points. This would be 0.5, comma 0, 2, comma negative 1, and 3.5, comma negative 2. Okay, our maximums and minimums. A maximum is where we have what looks like a hill because our graph is going up and then turns and starts going down. Minimums look like valleys. We're going down and then we switch to coming up. So what I would do is I would say max, and then I would put what point is a maximum, if there is one. In this case, 0.5, comma 0 is a maximum. And then I would look at min, and I would write what point or points are a minimum, which in this case we have 3.5, comma 0, comma negative 2. Okay, and then the other point isn't either one. So next we want to look at decreasing, and increasing. So increasing is where our graph is rising, which is right here, and then it starts decreasing, and then it starts increasing again. When we write these out, we just look at the x values. Increasing. Okay, so when we start off over here on the left at negative infinity, we're increasing. We increase until we get to 0.5. then we start decreasing. Well, then we increase again, so I'm going to make this U symbol to show that it's both of these. Then I go from 3.5 and I start increasing again until I get to the edge of the graph. So we're going to say till positive infinity. So then decreasing is the place in between there. So from 0.5 to 3.5, I am decreasing on this graph. The other option that we can have sometimes is a graph can be constant if it just goes straight across. So if that happens, you would put constant, and you'd put the interval it's constant on. If we are graphing a function, I just wanted to throw out there that you can always plug things in to x and make your own table of values, like if it's a pretty easy equation to do, or you can type it into y equals, and you can press second graph, and that will show you a table of values, so that when you graph it on your paper, you have some points to use to be accurate with. Even, odd, or neither functions. A function is even if it yields the same result whether you put a negative or a positive number in it, and its graph is symmetric about the y-axis. An odd function yields the negative result if you put in a negative number, and its graph is symmetric about the origin. And then neither means that you get two different answers when you put in a positive and a negative of the same number, and it doesn't have symmetry in that case. So up here at the top we have f of x equals 3x squared. What I'm saying whenever on the previous slide is I'm going to put in a positive number like 1 and see what I get. And then I'm going to put in a negative number like -1. And I'm going to see what I get. If those give me the exact same number, it's even. If they give me the same number but opposite signs, that's odd. If they're two completely different numbers, then that's neither. So this first one gives me 3. The second one will also give me 3 because -1 squared ends up being positive. That means this is even. This graph, if we were graphing it, is a parabola. And so hopefully you can see how, if I had a more accurate drawing, that this would be symmetric on the y-axis. Okay, on the second one, I can do the same thing. I can plug in a 1, and I can plug in a -1. But this time, because it's cubed, the first one I will get 2, the second one I will get -2. Well, those are the same number, but opposite signs, so that is an odd function. What that looks like, since it's symmetric about the origin, is you have one thing that goes up this direction, you have the thing that goes down here. It's kind of like rotational symmetry, that the top right, if you rotate it around, looks like the bottom left. On this last one, if I plug in a number, hopefully you guys can see, like if I plug in 1, I'll get 2 for the first part, 3 for the second part. That adds up to 5. If I plug in -1, I'll get -2, but I'll still get +3. So that gives me -2 plus 3 is 1. Those are completely different, so that's going to be a neither function. And that function would not have symmetry like the last ones did. Vertical and horizontal asymptotes. On vertical asymptotes, you want to factor, cross out anything you can, and set what is left on the bottom equal to 0. Horizontal asymptotes, you need to look at the highest power on the top and the bottom. If the numerators has the smaller power, then you have a horizontal asymptote at y equals 0. If they're the same, you're going to grab the numbers in front of the highest powers and make that your asymptote. And if the numerator has a higher power, there's a slant asymptote, which is completely different and we're not really going to talk about right now. So on this first one, if I want to find the vertical asymptotes, that's where the bottom equals 0, which would be at x equals 2. Then I would look and say, well, my powers here are the same, so I'm going to take the leading coefficient on each one. That would be 3 over 1, which is 3. So my horizontal asymptote is at 3. This bottom one, I would need to factor on the top and the bottom to see if anything cancels out, because if something cancels, it's not a vertical asymptote. And I factored on the bottom there the difference of two squares, which hopefully you guys will start to recognize that you can use that. My vertical asymptote is at x equals -2. Since my powers are the same on the top and the bottom, that means that I have a horizontal asymptote at y equals 0. Okay, so that is the end of this section.